We shall start our first problem solving session for this course today. I am Clarice Nia Varghese. I am a PhD student in IIC Bangalore. And I'll be discussing a couple of problems that is relevant for that particular week's syllabus at every Monday 6 p.m. Yeah, so I'll start with a couple of problems that I have prepared and come up with. Then we'll go on to any specific problems that you may have. Okay, so the one other thing that I would like to let you all know is that the meeting is being recorded and this will be sent to the NPTEL committee for their evaluation and all. So the meeting is being recorded. Okay. So yeah, if you have any problems, any questions in between the problem solving session, you can unmute yourself and let me know. Yeah. So in the lectures we had seen that spectroscopy is the study of interaction of light with matter. By light we mean about electromagnetic radiations, and these electromagnetic radiations can exhibit dual behavior of wave and a particle. The characteristics, the properties that wave properties of electromagnetic radiation includes reflection, refraction, diffraction, interference, and polarization, whereas the particle nature of the electromagnetic radiation uh, 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 results in reflection, refraction, photoelectric effect, and Crompton scattering. This has been already covered in the lecture. I'm just listing the different properties exhibited by wave and particle nature of electromagnetic radiation. So the wave characteristics is defined by wavelength, wave number, period, frequency, amplitude, phase, and velocity. These has been explained in the lecture. Let's go over a problem which is focusing on this region. So if you have to calculate the number of a beam of IR infrared radiation with a wavelength of 5 micrometer, how do you calculate? So we have been given the wavelength lambda is equal to 5 into 5 micrometer, and this corresponds to 5 into 10 to the power minus 4 centimeters, and the wave number nu bar is equal to 1 by lambda, where lambda is given by 5 into 10 to the power minus 4. So this is 1 divided by 5 into 10 to the power minus 4 centimeter. So this is equal to 2000 centimeter inverse. So the wavelength corresponding to the wave number corresponding to a beam of IR radiation with a wavelength of 5 micrometer is 2000 centimeter inverse. In the lecture we have been also introduced to the particle properties of electromagnetic radiation. So the particle nature of light is denoted as the photons is coming with the pockets of pockets of energy, and we relate energy of every single photon to its wavelength, frequency or wave number. So the energy of a single photon is given as hc by lambda, where c is the velocity of light and lambda is the wavelength, nu is the frequency. We can also write this as hc nu bar, where nu bar is the wave number. So from this part, there is a question that we can solve now. It's about to calculate the energy in joules of one photon, uh, of one photon of an IR radiation with a wavelength of 5 micrometer, and this can be calculated as E is equal to hc by lambda, where h is Planck's constant. H is Planck's constant. So h is equal to 6.626 into 10 to the power minus 34 joule second, where joule is the uh, units of energy, and c is velocity of light, that is 3 into 10 to the power 8 meter per second. Lambda here, lambda which denotes the wavelength here is 5 micrometer, that is 5 into 10 to the power minus 6 meters. So E is equal to 6.626 into 10 to the power minus 34 into 3 into 10 to the power 8. This is in joule second, this is meter per second, and lambda is 5 into 10 to the power minus 6 meters. So this we can cut off meter with the meter in the numerator, seconds and second inverse will cut off, and when you do the math you will get the energy value as 3.98 into 10 to the power minus 20 joules. Okay, then yeah, so we had seen how the interaction of light with matter happens. There is a low energy ground state and a high energy excited state, and we stimulate the analyte to undergo a transition from ground state to the excited state, and we detect the electromagnetic radiation emitted while the analyte is coming back from the excited state to the ground state, and this can the energy of the energy gap between the ground state and the excited state, we can calculate the frequency the energy of the electromagnetic radiation that comes out, from which we can calculate its frequency or its wavelength. So we have a wide range of frequency which we observe in an electromagnetic spectrum, and starting with a lower frequency, we have radio waves, followed by microwaves, followed by IR, UV, X-rays, and gamma rays. The wavelength increases in the reverse direction, where the higher wavelength is observed for the radio frequency waves, whereas the higher frequency is observed for the gamma rays. And using this different frequency of electromagnetic radiation has been used in different spectroscopic methods, ranging from gamma ray spectroscopy to NMR spectroscopy. So gamma rays has been used in gamma ray spectroscopy. X-rays are used in the X-ray photoelectron spectroscopy. UV and visible the radiations in the UV and visible range is used in electronic spectroscopy. IR is being used in vibrational spectroscopy. Rotational spectroscopy utilizes microwave radiations, and NMR uses radio frequency waves. Let's go over a question where we have been asked we have been asked to find the wave number and frequency ranges from a given a wavelength range. So if a sophisticated UV ultraviolet visible near IR instrument has a wavelength range of 185 to 3000 nanometers. And what are the wave number and frequency ranges corresponding to that? So the wave number nu bar is given by 1 by lambda, and frequency is given by nu is given frequency nu is given by c by lambda, where c is the velocity of light, and it is given as 3 into 10 to the power 8 meter per second. Okay, so for lambda is equal to 185 nanometers, that corresponds to 185 into 10 to the power minus 9 meters, or 185 into 10 to the power minus 7 centimeters. Nu bar is equal to 1 divided by 185 into 10 to the power minus 7 centimeters. So this is equal to 5. If you do, when you do the math, it will be 54054 centimeter inverse. Frequency nu is equal to 3 into 10 to the power 8 meter per second divided by 185 into 10 to the power minus 9 meters. So this will gives us this will gives us 3 divided by 185, so 0.017 into 10 to the power 17. So these two be meter and meter will just cancels out, and this will be like 0.0162 into 10 to the power 17 second inverse. So this can be written as 1.62 into 10 to the power 15 hertz. Second inverse is can also is also in hertz, so we can just write it as hertz. So if you look at for the wavelength 3000 nanometer, for lambda is equal to 3000 nanometer, which is 3000 into 10 to the power minus 9 meter, or 3000 into 10 to the power minus 7 meter. Nu bar is given by 1 divided by 3000 into 10 to the power minus 7 meter. This can be written as 1 divided by 3 into 10 to the power minus 4. This is in centimeters, sorry. This can be, when you do the math, you will get 3333 centimeter inverse. The frequency can be calculated by 3. Nu is equal to c by lambda, where c is 3 into 10 to the power 8 divided by 3000 into 10 to the power minus 9 centimeter. So this is 3 into 10 to the power 8 divided by 3 into 10 to the power minus 6. So this is in meter, this is in meter per second. So we can cut this both meters off, and this will be in second inverse. So we'll cut both 3 and we'll get 10 to the power 2, sorry, 10 to the power 14 hertz. So the wave number ranges 54054 to centimeter inverse, whereas the frequency ranges 1.62 into 10 to the power 15 to 10 to the power 14 centimeter inverse. Just like 10 to the power 15 to 10 to the power 14. Sorry, this is in hertz. Yeah. So the wave number that for which this wavelength range corresponds to is 54,054 to 3,333, and the frequency range is between 10 to the power 15 to 10 to the power 14 hertz. Yeah, there is one more question which I would like to discuss before coming to your questions. It is very simple, just to calculate the wavelength in centimeters given the frequency or wave number. So the wavelength, so calculate the wavelength in centimeters of an airport tower transmitting in 118.6 megahertz. So we know wavelength lambda is equal to c by nu, where c is the frequency of light, which is given as 3 into 10 to the power 8 meter per second, and wavelength lambda is equal to 3 into 10 to the power 8 divided by 118.6 megahertz. So 1 megahertz is equal to 10 to the power 6 hertz. So this can be written as 3 into 10 to the power 8 divided by 118, okay, meter per second, 118.6 into 10 to the power 6 second inverse. So this will be, when you do the math, this will be, okay, first let's finish off the 10 to the powers. So this will be 3 into, this will go to 2. So this is 3 into 10 to the power 2, 10 to the power 2 divided by 118.6. This is in second inverse. This is meter per second. We can cancel per seconds from numerator and denominator. So this, when you do the math, it will come to 2.52 meter, which corresponds to 252 centimeter. The next question is to find the wavelength in centimeter for a radio navigation aid transmitting at 114.10 kilohertz. So lambda is going to be 3 into 10 to the power 8 divided by 114.10 kilohertz. This is in meter second inverse, and this is 3 into 10 to the power 8 divided by 114.10 into kilohertz is 10 to the power 3 hertz. 1 kilohertz is equal to 10 to the power 3 hertz. So this is 114.10 into 10 to the power 3 hertz is second inverse. So we can cut off these two, and once you do the math, it will come to 2.6 into 10 to the power 3 meters. This will corresponds to 2.6 into 10 to the power 5 centimeter. Okay. The next is to the um, find the wavelength in centimeters for an NMR signal at 105 megahertz. So 1 megahertz corresponds to 10 to the power 6 hertz. So lambda can be calculated as lambda is equal to C by nu, where nu is 105 hertz. So C is 3 into 10 to the power 8 divided by nu is 105 megahertz. This is in meter second inverse. So 3 into 10 to the power 8 divided by 1 megahertz is 10 to the power 6 hertz. 1 hertz is equal to 1 second inverse. So this is second inverse. Yeah. So this will be 3 into, when you cut this off, this will be 10 to the power 2. So 105. Second inverse we can cancel. This will come down to 2.86 meters. This will be 286 centimeter. Okay. The last one is to find the wavelength in centimeter for an IR absorption peak with a wave number of 18.1210 centimeter inverse. So wavelength can be calculated from a wave number using this formula, where wavelength lambda is equal to 1 by nu bar, where nu bar is the wave number. So this is 1 divided by 1210 centimeter inverse. So this is 8.2 into 10 to the power minus 4 centimeter. Yeah. So these were the couple of questions that I wanted to discuss today. If you had any problems with any of these questions that I have discussed today, I would like you to unmute yourselves and raise your questions. And if you have any other questions in general, I'm open to answer any of them. Am I audible? Yeah, please. If you have any questions. Sorry, one person. I can't see who were asking the question. Can one of you unmute and raise your question? It would be great. I will also I can also answer the questions if you can type out in the chat box. That is also fine with me. I can see the person whose name has been the list as BC is unmuted his audio, but I can't hear you. If you have any question, can you type out in the chat box? I can wait here for a couple more. Yes. Tell me. Which this question, right? Okay, here, right? Okay, one second. Let me also. No, it should be this one, right? This last one, right? How 8 plus 6 is 14, right? Yeah, yeah, no problem. Yeah. May I know who has asked me the question? Oh, sorry. I can't see the list of uh, participants, so that's why I'm sorry. Yeah, no problem. Yeah, Shubhadeep Mondal has a question. Um, if we consider interaction of electromagnetic radiation with cells, molecules, tissues, will it be different for each cases? Um, so yeah, so depending upon how different is your matter, the interaction is going to be different. Frequencies at which it the frequencies at which so basically, yeah. Okay. Yeah, so depending upon what is the matter that you're going to look at, the ground state and the excited state will be different. Ground state and excited state will be different. The ground state for something in a cell will be different from a ground state in the um, in a tissue or in a molecule or in an atom, which I think the sir will be covering in the next few lectures. And in the excited state also will be different, in which case the delta E will be different, which will eventually affect your the frequency or the wavelength of the electromagnetic radiation that it emits out, which will help us in distinguishing what sort of a molecule was it, what sort of a cell line was it, what sort of a tissue was it. So the primary purpose of the spectroscopic methods is to identify the properties of matter, to identify the characteristics of one particular molecule. So the interaction of light wave with different types of matter will gives us different characteristics, which helps us in distinguishing what is the molecular characteristics, what is the structure, what is the structure, what is the dynamics that has been shown by the system that we are studying. So yeah, it will be different, but you will come to know how different it is. Why is it? How is it helping us in understanding in understanding about the system itself? We'll get to know in the upcoming lectures. I'm sorry. Yeah, if anyone else has any question, please feel free to put it in the chat box. Or you can also unmute yourself and ask the question. I hope all of you were able to follow the questions that has been covered in the covered today. If you're not able to do it, please let me know. I can repeat any of the questions that you would want me to do. Sure, I'll be sharing the PPT with all of you, and the meeting is being recorded, so the recording will be shared with you also. The presentation slide will also be shared. Hi. Yes. Are you talking about this question? The question, okay. Are you talking about this question? Okay, 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 okay. So, yeah, okay. So if that was the case, it is somewhere here, right? 10 to the power 14 to 10 to the power 15 hertz in frequency. We were talking about a UV visible spectrometer, and the range of that UV visible IR near IR instrument was 185 to 300 nanometer. And if you look at in the nanometer range, it is coming somewhere here, whereas in frequency it is somewhere here. And you can screen over different frequencies which is labeled in the top, and you can also screen over different wavelength that is given here. This is wavelength, whereas this is frequency. Yeah. I think in the lecture videos also you have been given an electromagnetic spectrum. Yeah, anyway, the slides will be shared. You can have a closer look when you have it. Any other questions? You can type out your questions in the comment box, chat box. If you all don't have any more questions, shall we end the session? Or any one of you have any more questions? Shall we end the session for today? Okay. Thank you all.